For coming this early. I'm glad you guys are here to kind of learn a little bit more about networking. So with networking, that's where in the past, it's something that we didn't really have to deal with knowing how to troubleshoot our production networks. We kind of designed systems where we had a lot of things that were point to point. So we had analog audio, we had SDI, MADI, all of these signals where if it didn't work, you just have point A to point B. Am I getting signal? Is it working? What's going on? So now, in the last 3 years especially, I would say, we've kind of moved to really flexible IP networks for everything. So this has a lot of benefits. For example, say you're doing a shoot in your lobby, and you need lighting control, you need video, you need audio, you need intercom. What you can do now is you can just run that over a single network cable and break that out. So we're adding a lot of flexibility, but with that, we're adding some complexity. It's a different way of troubleshooting. It's a different way of thinking about things, and we need to know how to build stable production networks. So that's one cool part of you guys being here is kind of learning that skill set. Because for me, I was an audio guy originally. That's where I started. But for all of us, I think, we've had to really learn the IP and IT side a little bit to do our jobs. And it's kind of been a little bit forced upon us, but it's something where it adds a lot of benefits to what we do. So we're going to kind of go through a few different things today. We're going to start really basic, which might be a refresher. We're going to start kind of with our physical connections of how those work with copper and fiber optics and things like that. And then we're going to work our way into what happens inside the switch, how are packets moving around on the network, kind of a basic introduction to IP networking and the different layers of that. And then finally, we're going to talk about different types of media protocols that we use. So Dante, NDI, different things that we use on a day-to-day basis. So starting out, we're going to start out real low. We're going to start out with the basic network cable. So you guys are all familiar with a CAT cable. We're not going to spend too much time on it, but basically the main thing to know is your different types of network cable. And the biggest thing with that is going to be speed and distance. So for the most part, we use Cat6 cable for everything that we do. But now we have some higher bandwidth things for video storage, edit networks, things like that, where we're using Cat7 or Cat8 cable. One thing that's really interesting is that Cat7 is not actually a real standard. So basically, they skip from Cat6 to Cat8, the IEEE, the organization that does that. So one thing with that we're going to show in a second is 100 meters is really your max length for a CAT cable. And that's where you guys can have intermittent issues and packet loss and reduced bandwidth and things like that if you exceed that. So the other thing is just shielding. As you get up into some of the higher bandwidth cables, that's where you start to have foil shielding because your tolerances are a lot tighter, and it also helps with RF interference and things like that. The last thing to note with that is that there were two different wiring standards for CAT cables. So there's an A and a B standard. And this kind of started when we had computers and switches, and they wouldn't sense the type of device that they were connected to, so you had to use these things called crossover cables and things like that. But now things are auto-sensing, or auto-MDIX is what that's called. So you just have to worry about, if you are making cables, use the B standard. It's what the rest of the world uses, and you'll be good to go. So what does that practically look like for just making sure you have a base level cable that's working? So we have a couple different things here, a couple different tools that hopefully you guys have these already. I'm going to show you quick a continuity tester. So we have a big old long cable here. And this is something that you can get at Home Depot, Amazon. You can get them for 20 bucks. So if you don't have one, you absolutely should. So this guy's showing us, hey, we have our pin out and all the pins are connected, which is great. But what if you have a pin out or a cable that tests fine for a pin out, but you're still having issues? So I want to do a quick demo of the length talk that we had before. So this cable that I have is over 300 feet. And what you're going to see when you guys have a cable that's over 300 feet is you're going to start to see packet errors, and you're going to start to see reduced speed. So right here, this is a cable tester that's showing us our cable is good, but our speed that we can actually handle on the cable is reduced down to 10 megabits a second because we're over 300 feet. The other thing to keep in mind with that is that a lot of you guys, and I use these too, use these slim run patch cables, which are awesome, super cool. But these reduce your overall cable length more than the length of the cable itself because it's a thinner gauge wire inside of it. So like a 3-foot patch cable is actually going to reduce your usable length by about 10 feet. So kind of triple the length of your cable when you're using these slim run patch cables, to keep that in mind. So those are kind of your basic cat cable skills. And again, feel free to jump in with questions anytime during this. One other quick note is just labeling. Again, it's the simple things that help you build up a large-scale network, and labeling is going to make your life way easier for troubleshooting. So don't let your past self sabotage your future self, is my motto.
There's a few other things, not just related to length, that can cause that same result of cables failing if there's too much, we call it EMI, electromagnetic interference. Like if a cable's running along with a bunch of extension cords, for example, the same way you get a buzz like in a mic cable, that same buzz causes problems with networking as well too. So just because it passes a continuity test with a normal tester, may not mean the cable's 100% good.
Yeah, yep. But kind of starting out, that's where that continuity test is going to be most of your issues. And then if you need to dive in more, that's where there are tools to do that. The other thing with copper cabling is PoE. So we have a bunch of devices here. We have these cameras, we have a speaker, we have Dante devices. So that copper cable can carry PoE. And the main thing to remember with that is just matching your switch type to the devices that you're using. So we're seeing a lot more PoE++ devices, like PTZ cameras and things like that. So just making sure that your switch can handle those PoE++ devices. And again, a higher power switch can handle lower power devices, but not vice versa with that. The other thing I want to spend a little bit of time today on is just giving you guys a basic knowledge of fiber optics. So as we get into more higher bandwidth devices, that's where it's kind of requiring us to use fiber. But fiber is becoming a lot cheaper, and the tools to troubleshoot it and test it are cheap as well now. So before, like, I don't know if you heard that fiber is expensive to terminate or expensive to have the test tool to test it. That's not the case anymore. For the most part, you can have the tools that you need for 15 to 20 bucks a piece as well. So looking at fiber, we have two main different types of fiber. We have single mode fiber and we have multi-mode fiber. So single mode fiber is a single mode of light down the fiber cable, whereas multi-mode cable has multiple modes of light kind of bouncing down the cable. And multi-mode uses cheaper optics like LEDs to do that, whereas single mode fiber uses more expensive optics like lasers. In the production world, that's where I'd really recommend single mode fiber is kind of your most future-proof investment with that. Most broadcast equipment, if you think of like an SDI to fiber converter, something like that, that's where that's going to use single mode fiber by default. The only thing that really uses multi-mode fiber in our production world is going to be something like Digico audio consoles or Yamaha or things like that. And the biggest difference, again, with that multi-mode fiber is it's a bigger core on the inside to be able to support the multiple modes of light. So kind of your basic fiber structure, which we'll see. We'll take a look at that under a microscope here in a second. We have our core, which is basically really tiny, smaller than your hair. Cladding, we have a strength member for pulling, and then your outer jacket. And there's a few different types. You have your thin cables, like these little guys, or we have thicker tactical fiber cables that have metal shielding in the jacket, or even thicker than that, where you can run them over with a forklift or string them between light posts. So as far as fiber being fragile and things like that, there are options that are really robust. A couple of connector types that you're going to run into. So LC is going to be your most common for data networks, for switches and things like that. We'll look at SFPs here in a second. And then SC, you don't see as much anymore. ST is super common in the broadcast world. So if you think of like a NBC sports truck that pulls up to an arena, it's going to be a ton of ST fiber. just because, again, you have a locking metal connector on that, and it's a little more robust connector. The other thing that we're using a lot is MPO, or MTP fiber. So this is a way to send between 8 and 48 strands of fiber down a single cable with a single connector. And the cost of that is also not crazy expensive to get pre-made assemblies. We saw kind of two different color connectors. So one thing to keep in mind, we use in the production world mostly UPC connectors, which is a flat cut. There are these green connectors, which are APC, which you can't intermix with UPC. So just making sure that you buy the connector type you want, and then the end face cut that you want with that. So APC connectors basically are cut sideways when they mate together, and that's to break any sort of reflectance or reflections coming back down the fiber. So it's used a lot in RF or like long distance fiber runs, like fiber to your home is going to be an APC connector. And then in the production world, we have tactical options that are really robust and pretty bulletproof. I'm going to pass this around if you guys want to take a look at that. So we have optical con connectors, which are self-sealing. So these guys keep dust from coming in the connector. There are some little flaps that open up when you plug them in, and it keeps you from having to clean them as often. And then we also have camera fiber. SMPTE LIMO is pretty common. And then like Opticore HMA, that's what we use for Digico consoles as well. So we have our cables. What do they plug into? So we use a thing called SFPs in a lot of our devices. So going back to like this fiber to SDI converter, that's where you have a little SFP that plugs in. And there's a bunch of different types of SFPs. So SFPs can do more than just network. An SFP is basically anytime you're doing electrical to optical conversion. So like from the network switch electrical to light to go down your fiber cable. And these guys are swappable. So when you buy a switch isn't necessarily going to come with a fiber port on it. You're going to have to buy some SFPs. And there's a few different types. So SFP and SFP plus, kind of your different ratings are based on your different speed. And then you can buy SDIs or SFPs for SDI or cat cable or things like that. So how do you troubleshoot fiber? How do you get kind of those baseline skills for troubleshooting? So there's a bunch of now super cheap tools that help you do that. So the first thing, if you guys do use fiber, it's called a VFL. So a VFL is a visual fault locator. And again, it's a $15 or $20 tool. What this does is basically plug it in on one end and then make sure you're getting light out the other end. I don't know if you guys can see that. Yep, on screen. The other thing that this will do is it'll show you if you exceed the bend radius of your fiber. So if you can see, I don't know if you can see the fiber glowing in there when I bend it. So that's unbent. And then when you bend it, it starts to glow. And I'll pass this guy around too. So that shows you, again, when you bend a fiber too much, you're going to lose light because it's exceeding the radius that the light can bounce within the fiber, and it's basically bouncing out of the fiber at that point.
So that fiber is not necessarily broken, what he did right there. It's just, it's bending too hard.
Yeah, it's bending too hard. Yeah.
When you do have a broken fiber, though,
Yeah.
you can use a VFL, and it will be very bright on that jacket, wherever that break actually has happened.
So we'll pass this around. Feel free to bend that fiber. If you break it, no problem. Go for it. Next kind of easy tool is if you're getting light down a fiber, then how do you know if you're losing too much light? So you use a tool called an optical power meter, and it's kind of like a dB meter for audio, but for fiber optics. So again, these two examples right here are really cheap examples off Amazon. So these guys will show you, this will generate light, and then this one will receive on this end. And that's where I can really easily see, hey, am I getting too much loss on this fiber cable? So on this guy, we can see we're getting, I think I'm on the wrong fiber. Nope. Yeah, this one we're getting only 0.8 dB of loss. So that gives you kind of a good test. If you have more than 6 dB of loss on a cable, that's where you're probably going to start to have issues depending on the device that you're using. So kind of those two sets of tools set you up for success with fiber. And again, they're only 15 to 20 bucks a piece. If you have fiber that's really lossy, how do you deal with that? How do you clean a fiber? So I'm going to show you guys quick on here. I get to use Apple Photo Booth. Go back in time. So this is a fiber microscope. So what this shows is it shows me the end face of the fiber.
Scoot back
So
here,
we're going to
covering up
focus
the
in on
camera.
that. Yeah. So there's our fiber end face. So what we're actually looking at right now, the dark part is going to be the cladding, and that little dot in the center is the core. So that little dot is actually where the data is being transmitted. And that's critical that that doesn't get dirty. So what happens, and this will be kind of gross looking, but if I rub that like on my arm or on my face or something like that, and then plug it back in, we're going to see a real crusty and nasty fiber right there. Yep, yeah,
So
gross. Little petri dish of goodness. So this is what causes issues when you guys have fiber issues with a cable not working. So that's where cleaning your fiber is super important. And again, super easy tools. I feel like I'm a salesman for Amazon. Oh, right here. Again, 10 bucks, 12 bucks. The Cleatops ones are a little more expensive. But this is just a fiber little clicky stick or IBC pen. Just grab this guy, give it a couple clicks, and then we'll patch that back in. Or you can use this Cleatops. Just give it a couple swipes on that. And we look back at our fiber. Need to do a couple more.
So what's happening in these tools, they both do it differently, but there's either a piece of fabric or a string that every time he clicks that down, it's advancing to a new clean piece of string, right? So just wiping the ends of those fiber off. So there is, on both of them, there's a limited number of clicks, if you will, you have. It's an expendable thing you have to replace every so often.
Yeah, but you get quite a few uses out of that.
Yeah.
So that kind of shows, again, cleaning fiber. So the main point that I wanted to get across is using fiber is not scary. The tools to use it now are cheap and easy. And then cleaning fiber, you guys can do that super easily as well.
Yeah, cheap enough to the point, like a lot of times when we're doing installations, fiber or whatever, like it's just good habit to, before you plug in a patch cable, go use, we call them click sticks, go use a click stick on it, right? Just know it's clean. You don't necessarily have to get a microscope out every time and figure out, is it dirty, do I need to clean it? That's so cheap, just clean it every time.
Yeah, and if you want to make sure something works, like when I'm working on like a broadcast TV truck, I'll just keep this little power meter with me and make sure I have good fiber signal when I'm setting up a camera or a switch or something like that, or troubleshooting that. Cool. So that's kind of the basics of kind of the physical devices that we use. Let me flip back. So yeah, just to kind of go over that again, we looked at the core of the fiber versus the cladding, and we looked at it under a microscope. So now that we have our devices connected and we have the blinky lights, step one. How does that traffic move through the switches on our network? And for me, that was a mystery for a while as an audio guy. But again, as we've had Dante, we've had all these different technologies come about, we have to learn these skills to be able to troubleshoot it. So we're going to start with kind of something from the IT side of things. So you guys might have heard of layer 1, layer 2, layer 3, and onward. On the AV side, we're really focused just on layers 1, 2, and 3, kind of your base layers of how does data move from point A to point B on the network. So the higher layers are going to deal with applications and sessions and web traffic and things like that. So layer 1 is your physical layer. And that's what we just talked about. So optical cables, Ethernet cables, Wi-Fi, things like that, kind of your physical layer of how data is moving. Layer 2 is going to be your local network. So think of this as you plug in a bunch of Dante devices to a switch, And the traffic is just living within that little network. You're not going outside of that network to another subnet, and you're not going out to the internet. All that traffic is living in layer 2. Then layer 3 deals with when we need to move things between networks. So say I have a lighting network and an audio network, and I want to be able to route and talk between them without bridging all the traffic. We'll talk about different types of traffic here in a second. That's where we use layer 3 or IP technology for that. So starting at layer 2, that's where devices have a MAC address. So a MAC address is a physically burned-in device that's unique to every single device that you buy. And you'll see a MAC address, like I have a little Wi-Fi router here. If you look at the sticker on it, it'll show you the MAC address, things like that. So the MAC address is just a unique identifier that's burned in. And it's going to be a 48-bit hexadecimal number. You'll see it like 00, 1A, 2B, so on and so forth. And again, what's interesting too is the first half of that MAC address is going to identify who manufactures that device, and then the second half is going to be a unique identifier to that device. So later on we'll show that you can scan your network and see devices and their manufacturers pretty easily, which also helps with troubleshooting. So the next step from that, you have your burned-in MAC address, which you can't change, and then you have a logical IP address that you assign to your device. So an IP address is written in binary, and this will kind of help a little bit later on as we talk about subnetting. So you have 4 octets. Each octet is 1 byte. 1 byte is 8 bits. So the octet is basically made up of your 8 bits that can either be on or off. And the easiest way to think about that is think about your old school DMX fixture. I don't know if you guys ever use these, basically where you would set your DMX address with a dip switch. So your combination of whether bits were on or off made your number for that. But with DMX addresses, you don't have a fun switch, or IP addresses. So we have our MAC address, we have our IP address. So how does that data look when it moves across the network? So our data is moving in packets. So a packet is going to contain your information that you're trying to send, like the letter inside an envelope, and then we're going to put a header on top of that, or the information that it needs to move across the network. So the header is going to have your destination IP address, source IP address, and a bunch of other information that that packet needs to move across the network. And then once it gets to the end device is going to remove that header and then use the data within that packet. So again, that header is just information for traversing the network. So we're going to kind of demo quick using a simulation software. What does that look like on a network? Here we go. All right, so we have a bunch of devices connected to a network switch. So what is that network switch doing to know where to route those packets on the network? That network switch is actually building a table of all of the MAC addresses of the devices that are connected to that switch. So anytime a packet comes in, the switch is registering that and building a table. So right now, if we go on here, we're building this MAC address table, and right now it's empty. So this is kind of an old school switch where I have to look at the CLI to do commands. We're going to look at more visual options later on. But right now, there's nothing in this table. So we go back to our network, and I'm going to send a ping . So I'm going to generate this ping packet. And ping is basically saying, hey, does whatever device with this IP address exist on the network? So right now, our switch hasn't heard anything from any device on the network, so it doesn't know where to send that ping packet. So what it's going to do, and again, this is also called an ARP packet of trying to discover who has that IP address. Since it doesn't know, it's going to flood that out to every port on the switch except for the port that it came in on. And then our device that has that address, we saw these 2 devices are not going to respond. The device up there that has that address will respond and then go back to this PC. And now that the switch knows that these 2 devices are connected, as well as the devices know the MAC address of the other device on the network, now packets are going direct point to point between those two devices. So if we look at our switch again, and we look at our MAC address table, the switch is learning the MAC addresses and what port that MAC address is connected to. So as soon as you plug devices in, they're starting to send packets. It's not a perfect world like these devices in a simulation where they're quiet and not sending anything. So from the moment you plug something in, your switch is learning that, it knows what devices are there, and that's how traffic is routed or kind of sent around a network on the basic level, so in like a basic Dante network. It's actually using MAC addresses and not IP addresses to do that. IP addresses, again, are just logical addresses that you give to devices, and they're used for routing outside of your local network, or as a logical way for you to connect to a device by typing that in your web browser.
There are entire systems that don't, that are, we call them layer 2 only. They only use MAC addresses. The devices don't even get IPs. A lot of lighting stuff, actually.
Yeah, lighting, Wave Sound Grid is a perfect example of that. So if you think of waves, how it doesn't matter what IP devices you give it, things just pop up and work. It's because it's using MAC addresses only for that. It's layer 2 only.
There's some advantages to that too. Like there are cool tools like for some camera manufacturers that will allow us to set up a camera even though it's at an IP address that's completely different than what my computer is at, different range. You do it all by that layer 2 routing.
So yeah, we saw a couple different types of traffic in that demo. And this is really important to understand your types of traffic on your network when you're dealing with AV devices. So unicast is your basic point-to-point, one-to-one type of traffic. So after we saw those two PCs in the simulation know where each other were on the network, and the switch was sending that traffic properly, the packets were just going from one port to the other. They weren't going to any other ports on that network switch or getting sent to devices that didn't need it. And that's unicast traffic, or one-to-one, point-to-point. We also saw an example of broadcast traffic. So this is kind of the spammy traffic on your network. So broadcast is basically one to everything. So when you start to grow your network, if you keep growing your network and don't subdivide it, that's where you'll start to see devices getting slow, because something like Kyle and I were talking yesterday about like Apple TVs announcing themselves on the network. That's how your computer sees it as an option to AirPlay to, but it's basically just sending out those broadcast kind of spam packets on the network, and your Shure wireless mic has to filter through all of those packets before it gets to the packet that it actually needs. And the more devices you add, the more overhead that adds on the network. And that's when you start to see things getting slow and getting laggy when you try to type in an IP address and go to something, or things just stop responding. I went to one church where basically the entire church was one flat network. So all their printers, their Dante devices, their computers, everything was just connected to a single network space. And with that, they were like, yeah, sometimes our TVs will turn off and on when we hit the command button on QSys, sometimes they won't. And basically, I isolated the TVs out, and I was like, hey, this works great. But when you add all that broadcast traffic in, the TVs were just freaking out and starting to lock up and slow down. So we're going to talk later on about subdividing our network to build that robust network where we don't have to worry about those issues.
Yeah, you can get to the point with broadcast traffic where you saturate the ability of a device to even receive as much traffic that it has to ignore, right? It's kind of like, I equate it to like, you know how you get tons of junk mail in your actual physical mailbox? You guys remember those things, right? Every time you go empty that thing, it's just a load of junk mail, right? There may be one thing in there you have to pay attention to, right? That's kind of how broadcast traffic works. It's everything on the network is announcing it to everything. So your devices have to go sort through, not for me, not for me, not for me, not for me, this packet's for me, not for me, not for me, this packet's for me, right? It's a lot of overhead on devices. And when we're talking Dante, I forget how many times a second do the clock announcement messages come out? What is it? 4 times a second, 10 times a second, whatever. Say it's 10 times a second, you have 10 devices. That's 100 packets every second that go out across your Dante network, right? And the bigger the network, the more and more and more of that broadcast traffic that happens that we need to, it's not bad, it all needs to be there, but we need to make sure we can manage that traffic properly. Otherwise, we're going to flood devices with too much information.
Yeah, so we're going to kind of talk about this concept of a broadcast domain, and that's how we divide up our network is into kind of different spaces. So we'll have a broadcast domain for all of our audio traffic, which is also going to be a different subnet VLAN broadcast domain to keep all of our lighting traffic within its own little world, and kind of divide up our network to make it and keep it stable as we grow things. The last type of traffic, which this is the most important type of traffic for AV, and this is what you guys hopefully can get a good understanding of, and that's multicast traffic. So multicast traffic is one to many. And what that means is that I can have, for example, a Dante device or a video encoder, and that video encoder is sending out one stream to 50 TVs in the building. So if I was using unicast traffic, I would have to send out 50 discrete feeds from that one device. With multicast traffic, that offloads that portion of it to the switch. So I'm sending a single multicast stream to the switch. The switch is identifying that as a multicast stream, and then it's filtering it to the devices that need that stream. So the technology that allows for that, the protocol is called IGMP snooping. And again, this is one of the most important things in most AV networks, if they work or if they don't work. So this is where you'll start to see intermittent Dante clock issues, or devices freak out and not work, or things like that. The first step is normally looking at IGMP snooping, and is that working correctly or not? So in this case, IGMP snooping is off, and that's where I have two devices that are each generating 800 megabits a second. So this switch has 1 gig ports, they're 1 gig endpoints. So when I try and plug in any receivers, they're just going to be overloaded with traffic, and they're going to shut down and stop working. I need a way to be able to manage that. So what managed switches can do, one of the features, again, is IGMP snooping, where the switch itself will actually go out and query the network. So it's going to ask each device on the network, what do you need for multicast traffic? What streams do you need? What Dante flows do you need? And it's going to build a table of what's going where, kind of like that MAC address table, except for multicast addresses. And now this decoder is going to ask for the yellow stream, and it's just going to get that. And it's going to be just fine. It's under the max of that port. The next one is going to ask for the green stream. Great, good to go. Likewise, and then the wireless mic on your network, it's not going to ask for any of those multicast flows, so it's not going to get anything. So everything is happy, and we're offloading kind of that routing onto the switch. And this is kind of how the best example of moving from like a big video router to in the IP world, your switch is managing a lot of that. And kind of that base protocol, again, is IGMP snooping. The other thing to keep in mind, and the biggest issue that I see on networks where you have, again, Dante is a great example, clocking not responding, things like that, is you need to have only one switch as your querier on the network. When you have multiple switches querying on the network, that's where then you can have one switch building a table over here of devices, another switch building a table over here, and not all the traffic is getting to the needed devices. So that's where IGMP snooping helps manage that. How does your switch know it's a multicast flow or multicast stream? That's where your different IP address ranges kind of define that, as well as MAC address ranges that go along with that. So the first kind of part to know is your private IP ranges. These are what we use to logically address devices. So 10 dot whatever, 172, a lot of you guys at home is 192.168, so on and so forth. But multicast devices use IPs in kind of that 200 range. So 224 or 239, those are going to be used for multicast IP streams. You also have your public IP ranges. The main thing to keep in mind with that is don't use public IPs on your local devices when you're configuring your network, because that can cause issues with finding other devices that use those same public IPs.
Yeah, you can look up on Google, wherever, there are specific ranges that are, they call them user-defined scope. So like you said, 192.168.10, 172s, whatever. The multicast is a specific user-defined scope range. So if you're not sure what addresses to use, just do a simple search for it. There are areas playgrounds you're supposed to play in and playgrounds you're not supposed to play in.
Cool. So the next thing is kind of the hardest thing, or at least for me it was the hardest thing to wrap my head around, and that was a subnet. So when you type in your IP address on your computer, that's where you have your IP address, and then you have that field below called your subnet mask. And what your subnet mask is doing is it's helping determine when your computer can talk directly to devices, like what we saw in that simulation earlier, or when your device or computer needs to go to a router to send packets directly to a router to then go to the next hop to get to Google or wherever it needs to go. So how that's determined is basically by, like those DMX dip switches that we saw before, turning off some of those dip switches. So for example, the subnet mask 255, 255, 255, that means all of our bits are on in the first 3 octets, and then that last octet is open for all of our devices on our local network. So anything outside of that range is going to be for basically that traffic will go directly to a router. Anything within that, that traffic will go directly to devices. So an example that we have is this network where we have 2 devices. So one device has 10.10.10.126, one device has 10.10.10.127, and our subnet mask is 255.255.255.0. So those first 3 octets, because all those bits are turned on, those addresses have to match. And as long as they match, our computer knows that it can send traffic directly from device to device. Another example would be 255.255.0.0. That means just the first 2 octets have to match. So just 10.10 has to match for the device to know that it can go on the local network. So another example of that is basically here, where I have my 2 computers. Say I'm sending something to 10.10.10.126. We know those first 3 octets match because our subnet mask is telling us that's our network space or network ID. And then our traffic is going to go direct from device to device. Say we have an address 192.168.1.123, or like Google DNS 8.8.8.8 or something like that. The first 3 octets don't match. So our device, instead of trying to send it directly to that IP address, it's going to send it to the router IP instead to get routed to whatever network it needs to go to, or the next hop to get to the web, or anything like that.
The router IP is also called the default gateway or gateway, whatever, different devices called different things, all the same thing. It's where do I go where do I send information if it's not on my local network? It's also, you guys may have seen times where the router may be blank on your computer or set it up on a device. That just means I have no intention of sending anything out to a different network or VLAN, and leaving that router blank is okay because we don't need it.
Yeah, so like on a basic Dante network, you don't need a router IP on your computer to access things because you're not trying to get out of that local network. The other thing
also,
I want to talk.
How many of us, I'm one of these, just put 255, 255, 255.0 because it always is what we always see and it seems to work all the time, right? JB, I see that hand.
So yeah, that's the most common range because that gives you enough IPs for 255, well actually 253 devices on your local network. Now you can again expand that space out by turning off more of those bits and give yourself 500 addresses or 1,000 addresses by kind of widening that range of host IDs. So we have both the way we IP devices and subnet it to divide things up, but then we also have what's called a VLAN, which is virtually dividing up our switch into basically, the easiest way to think about that is kind of separate switches on the same switch. So the case that we have here is switch A and switch B. So we have 2 different VLANs. An example would be a Dante VLAN and a lighting VLAN. So port 5 on switch A can't talk to anything on port 1 because they're on separate virtual VLANs. We've divided up our switch into separate virtual switches. The other thing with VLANs that this allows us to do is it allows us to tag that traffic on a trunk and send multiple VLANs down a single cable, and then on the other end, on a different switch, break those apart again without ever mixing together those two networks. So the VLAN is kind of the bucket that we put all of our devices in, and then the subnet and IP address range is the way that we logically address and divide up devices, so the devices know who they can talk to and where they can talk to. But then that bucket of the VLAN is kind of what contains that.
Just want to reiterate what he said one more time. It's when when we can send multiple VLANs across a single interface, a fiber, a Cat6, what have you, like you said, without combining them, right? The physical medium has nothing to do with the virtual medium, right? So we can send our Dante and video and lighting network from the main auditorium to the kids building, but I don't need 3 different cables to send those 3 networks. I can trunk those on one cable together. We just need to make sure we have the bandwidth to support the traffic we're sending.
Sending multiple things down one link. All right, so how does that relate to AVL networks, what we're building? So kind of just to start out, we have our baseline of managed switches and unmanaged switches. So an unmanaged switch is kind of like that Netgear throwdown 8-port switch that you guys have used for like waves or things like that. It doesn't give you the features that we talked about, like IGMP snooping or VLANs or things like that. It's just like in that first example kind of simulation, very basic point-to-point. It's learning MAC addresses, and it's sending traffic where it needs to go. It's not going to have any routing capabilities or even look at IP addresses at all. So again, for the most part, when you guys are building networks now, that's where you really, there's no other way to do it than with a managed switch. You need the features that that provides. So as we've seen stuff move to IP, in a lot of facilities, that's where we've seen the kind of different islands of networks. So in your room, you might have a lighting network, you might have a Dante network, you might have another switch for all your computers that connects back to your house network, switch for video devices or NDI or things like that. And it works. It's stable. It's easy. You don't really have to think too much about configuring things because each thing lives in its own world, which you're physically creating those broadcast domains that we talked about. But it's not very scalable, because then you start to have 5 switches in each location. On your stage, you're going to break it out again. You're going to have a Dante switch. You're going to have a lighting switch. You're going to have all these different things. So with the things that we talked about before, there is a way that you're able to combine those networks onto a single switch and VLAN it out into your different things, like Dante or lighting or your computers or things like that. But keeping those as separate broadcast domains and separate subnets. So this is kind of the way, as you grow and expand, you're going to have to learn how to converge some of those things unless you want to have separate switches for everything, everywhere. When we talk about AV networks, that's where there's sometimes a little bit of tension between talking, for example, with your IT staff about what they understand about networking versus what we need for networking on the AV side of things. Because in the IT world, it doesn't matter if it takes 2 seconds for an email to get from me to you. That's totally fine. But on the AV side of things, it really matters if it takes a second for it to go from my wireless mic through my audio console back to my in-ears on stage. You're going to have angry worship leaders, drummers that are just playing a whole different song, and it's not going to work. So we, on the AV side, try and minimize latency is going to be a big thing. And then managing that multicast traffic is a big thing that you really don't have as much of on the IT side. So we build our networks with as few switch hops as possible when we're talking about streaming media. Because each time a packet goes through a switch, it takes time for that switch to kind of process that packet, send it where it needs to go to the next switch. It takes a little bit of time to send it where it needs to go. So if you're daisy chaining all your switches together, that's where you're adding time on each hop, and you're going to see latency on your video streams or audio streams by doing that. So the way we design production networks on the simplest form is going to be having a core switch. So on larger networks, this is normally a fiber switch, like this guy right here. that just has fiber SFPs to connect to all of our switches in the field. And then all of our switches kind of star back to that one core switch. So that way you're no more than 2 switch hops away from any device on the network to minimize latency no matter where you are. And this kind of scales decently. On larger networks, you might move to a spine and leaf topology, but that's where on what you guys are kind of working on for Dante and NDI and things like that, kind of starting with a star topology is going to be a great place to be at. The other thing to keep in mind is bandwidth between your switches. So when I have 2 1 gig ports plugged into a switch, if they're going to basically devices on the same switch, it doesn't matter because most switches have a ton of bandwidth on their backplane to be able to route that traffic. The bottleneck is when I want to take a couple 1 gig devices on this switch and send it over to another switch on the other side of the building. Because I'm going to have 3 gigs of data coming in here, and if I run that out of 1 gig port, it's not going to work. So upsizing your links between switches to handle that bandwidth and kind of having an idea of how much bandwidth you're sending from place to place is helpful. So usually we recommend starting with a 10 gig link between your switches if you're doing multicast video traffic and things like that. Audio, you can definitely get away with a 1 gig link between your switches for sure. But when you get into video over IP, that's where having those larger bandwidth links, or if you want to plan for the future, having a 10 gig link between your switches is key. So who manages your network? And that's where I had ChatGPT make a nice image of a church network manager.
What was the prompt you put into ChatGPT to get that image?
Church IT, and then more churchy, more networky after that. Make that. So as far as who manages the network.
But that, I don't think everybody out here looks like that. I don't think it's wrong. Yeah.
I don't know.
We're much more diverse here than
Hopefully. So
gracious.
for your networks, you guys might have been in a case where you started where your IT kind of guy at church is providing your switches for your AV network. And that's where you guys might have had some issues with that because of the things that we talked about where the house IT side doesn't necessarily understand some of the AV needs that we talked about. So there's 3 different ways to go about it. Either your network is managed completely by you guys as the production team, or completely managed by the IT team, which I've seen both of those, or kind of a hybrid where you guys might manage the switches within your space, but then coordinating with your IT department or IT guy to link up for services like getting to the outside internet, printers, servers, things like that. Raining out there. So part of that is going to be coordinating with your IT team. So we talked about dividing up a network into different broadcast domains. This is what it normally looks like on a typical church that we work with. So we might have a production control VLAN, and in the simplest kind of world, we just link that directly with your house IT department, and they set up a subnet for you. They set up a gateway or router IP address for you, and then this gives you access to, they can set up a SSID, so you guys can have wireless access directly to your devices through the whole building, access to your audio console from an iPad, things like that. So kind of basic control of devices we'll put on a VLAN. But then our streaming media will separate out, and we won't link that with the house IT department. So this kind of gives you some reliability in that when your IT guys are making changes on Friday, you're not going to walk in and have your Dante network, your lighting, all that stuff not work unexpectedly because those aren't linked up with the house network. So this is kind of a happy medium where you guys don't have to worry about routing or things like that, but you're able to divide your critical media transport from your house IT department, but then also leave a VLAN that you tag or interface with your house IT department. So things that you need to talk about when you coordinate that in kind of this hybrid setup, talking to your IT department or IT guy about the subnet size, the amount of devices that you need, so they can assign you a range of IP addresses, the amount of VLANs that you want to interface with your house IT guy, routing, so routing between VLANs to different network storage or other devices. Talk about, again, Wi-Fi access is a great thing that I like to ask for because it makes your life super easy to not have to plug in to access any of your devices. And then quality of service. So streaming traffic, things like that, whether you're doing Resi or streaming to YouTube, Facebook, things like that, making sure that's prioritized with your internet connection in the facility over like your typical guest Wi-Fi, things like that. So those are some things to ask for. And kind of having the right language for that is going to help you guys have good conversations with your IT team. For switches, to kind of hit on what we talked about before, we have typical IT switches. So Unify is super common in churches because it's cheap, it's cool. I have it at home, it's really easy to use. They make great Wi-Fi access points, but it's terrible for streaming media. So the feature set for Unify is, again, great for the IT data side of things, but a great example is IGMP snooping. That's where Unify sort of gives you some controls for that, but I've had tons of issues anytime people have tried to put Dante devices or things like that on Unify switches because they don't have some of those things that you need for the AV side of things, which it's gotten a little bit better, but still avoid doing that. Meraki is another example, kind of those easy to manage IT switches don't necessarily play well with AV traffic. There are higher end switches that you can configure manually from the command line and things like that that work great. But kind of with some of those easy to use options, we've had issues.
It's worth mentioning too, like those switches, specifically talking about like Ubiquiti, Meraki, those kind of things right now.
Yeah.
Those are really good at doing, we call it SMB, small medium business, enterprise data networking. They're great at that. But what makes them super efficient at doing data networking also makes them not good for AV networking, right? So it's not a Ubiquiti bad, in this case Netgear good, right? It's from the design side, you got to take into account what are we using these switches to do and use the right tool for the right job, right?
Yeah, and again, like I have Unify switches in my bag because they're cheap and they're great. But when we're building these larger AV networks, especially if it's something where you don't have the deep background in IT, you want something that is reliable, something that's easy to use, something that's easy to configure. So you're just worrying about using the concepts that we talked about, not necessarily how to configure in depth from the command line and make those happen. So we've seen a lot of these AV-centric switches come out. So different manufacturers, L Acoustics, Yamaha has switches and dirt bikes. And we have Luminix, Pathway switches. One switch that we started to use a lot is Netgear. So again, for me, my view of Netgear was always the little 8-port blue switches. But Netgear has come out with a really solid product with great support on the AV side of things. We have Alex here from Netgear today as well, if you guys have any questions about that. And we really like them because the price point has come down to something that is affordable, and they're rock solid because they've taken the time to test.
Alex, when does the Netgear dirt bike come out?
2025.
Yes.
25, got it. You guys heard it here first.
Done.
Infocom, be there.
So yeah, these options have made it really easy for you guys as the production people to manage your production network. And we're going to show that here in a second. So we're going to show how easy it is to build a Dante network. And Kyle's going to show us that.
Okay, so real quick, just a brief overview of what we have here. Our friends at Netgear here provided all this hardware for us to demo with you guys. In the center here, you'll see this switch we have labeled Stage Core. That's this top switch right here, where all of the, we call them edge switches, all uplink either with a 10 gig, these first 3 are 10 gig uplinks. These 2 Cat6 cables are 1 gig uplinks. So mix and match a little bit depending on what switches are going where or what infrastructure we have. So generally this switch will be in, the rack room, control room, data closet, what have you, whatever the logical, physical middle of your network is, wherever, your fiber or whatever all runs back to, right? And then from there, we just have a bunch of different flavors of edge switches. There's 2 in this rack, 2 in this rack, and then there's 1 out there at front of house as well. We got a bunch of just generic Dante devices here we'll go over in a minute. We also have 2 cameras that BirdDog provided us for this demo. We're actually sending NDI from these cameras to the video switcher back there in the back over that uplink as well. That's all network, what you have been seeing Alex play with his toys here, right? So real fast, we've got 6 switches, but right now in the tool here, we only see 5, so we're gonna add the last one. This tool is called Netgear Engage. It's their management tool. It is a game changer for us, honestly. The most important button here is this top one. It says dark mode. Make sure that's turned on. Does anybody prefer light mode? Okay.
Oh.
You are dismissed. No, it's all good. You can turn it to light mode if you want your eyes to hurt. So under devices here, we've got all the switches that we've adopted into our site here. And then down here, we have one more discovered device. And all I'm going to do is onboard this. This could be a brand new out-of-the-box switch, never touched before. Obviously, I've set it up once or twice here. But literally, without logging into the switch, without doing anything, it just adopted it into our environment. It also would have updated the firmware to the current firmware. It set its authentication, changed the username and password and all that stuff into our site, which if you're using admin on your switches, let's have a discussion. We should not be doing that anymore. So now if I go back to topology, you'll see we have all 6 of our switches. So onboarding switches is literally that easy. That used to be a process for us of going with a console cable, physically connecting to every switch, and doing command line to get switches just configured and onto the network before we even start actually adding VLANs and stuff. So huge time saver, just right there, and we haven't even gotten to the good stuff yet. So I'm going to go to, let's see, let's go bottom rack, switch 2. Open this switch up, which this is this very bottom switch down here that the cameras are connected to. We can hover over devices or ports to see what's happening on these ports. I can see that whatever is plugged into port 23 has the IP address 192.168.20.101. We see its MAC address, and under received right there, which I can't point out because it disappears, but we see that port is receiving 379 megabits per second. This is this camera right here. It's sending 400 megabits per second of video out to front of house. We can also see on this port is the uplink, the port that's connected it to the core switch, which is why it says it's connected to stage core. We can also see the transmit rate, the data that's leaving that port is 369 megabits per second. So we can pretty quickly go, the video's coming in this port, the video's going out that port. If we go to the core, we'll see the same thing.
And one cool thing with Netgear is that a lot of those commands that you'd have to do by CLI, like setting up trunk ports and things like that, they're just automated. So Netgear has a feature called Auto Trunk. When I plug two switches together, it's going to automatically trunk all the VLANs between the switches. When I plug more than one link between a switch to another switch, it's going to automatically bond those together in a lag group and things like that that make it super easy, where you guys are just worried about the overall network kind of setup and how you subdivide it. This stuff, everything else is just kind of happening behind the scenes. But you also have the tools to dive in deep if you want to as well, which is super cool.
Yep. So again, just to finish that thought, we can see this is the port that the bottom switch is connected to. It's ingesting, receiving traffic at 371 megs, and then the front of house switch out there, I'm transmitting that at 371. So that's our one video stream moving from port to port to port to port through our network. The important thing to show too is if I go to any other switch, I do not see 371 megs a second because there's nothing on this top rack switch 2 that is requesting that NDI video stream, right? If I were to have my laptop connected to it and use an NDI monitor tool and view this camera, I would then see the data start moving to that switch because that is IGMP at work. That is my computer requesting a multicast feed from a device and the switch going, okay, I'm going to forward that traffic onto this port. Using the switch as the DA, if you will, the camera is not sending another feed out. The switch is replicating that feed. But just to hammer home this thought of multicast traffic, like when something is not requesting that feed, it is not sending that multicast traffic through those ports. If it were, we would saturate our network very quickly, and there would not be enough bandwidth to operate really. So you guys will see that, and there'll be how do I put it this way? So this Dante device, these little AVIOs, which you guys may or may not be familiar with, they're fantastic. The network chip in these is slow. It's only a megabit network chip, which is fine because it doesn't need to move. It can only do 2 channels of audio. It doesn't ever need to move a gigabit worth of data, so they put a cheaper network chipset in there. That's totally fine. These cameras or that NVX encoder is capable of moving 900 megabits per second. If I have multicast flooding every port, that one NVX encoder will be sending more data to all the ports than this is even capable of ingesting on an order of 10 times as much data as that device is capable of ingesting. So the symptom you'll see if multicast is flooding like that is my devices and Dante controller probably just disappear. I can't see them because it's getting yelled at so loud it can't even yell back, right? So again, that's just symptoms and reasons why we need to control the multicast traffic the way we need to control it. Any questions there so far? I know we've kind of been powering through a lot of this really fast, but yeah, go ahead.
I have a question. It's more of an engage question.
Uh-huh.
Is there an easy way to identify a switch through engage? I've kind of been
I know a guy.
Yes.
using fan speed and switch is the loudest. I don't know if there's actually a unique identify feature that I've been missing.
You mean like click a button and ID and make lights blink kind of identify?
That's in the roadmap right now.
Yep.
Yeah, definitely something that we've heard from installers and integrators around, so it's in the roadmap for sure.
Okay, that works. Thank you.
Yes, that will be a wonderful feature. One way when we're building a network like, at a church or what have you, one way we identify things quickly is when we're patching our switches into our core switch. We know, okay, kids room 1 is connected to, port 7, student room 3 is connected to port 8, whatever. And I can use this overview, if you will, in Engage to go, okay, that switch is MAC address ending in 624F03. And you can identify that, or even just by the IP address. You can identify the MAC and IP when it discovers down here. And I just know, based on where I physically connected it, which one these switches are. Alternatively, the other thing I think Alex and I both like to do is just plug one in, shows up, on board, name it. Plug the next one in, shows up, on board, name it. And then I just know which ones I'm plugging in as I'm onboarding them. So there's a few different ways to do that. But yes, blinky lights will be awesome whenever that.
Beautiful thing. I'm waiting for that feature too.
We like blinkies. Okay, so real quick, we're going to build a Dante network. Right now, all these Dante devices are not onboarded or haven't really done much with them. So we went to site settings here. I'm going to say create a new profile. And then pick these profile templates. These are really the game changer for what Netgear has created specific to AV. They've made templates that include all of the proper settings for whatever type of AV traffic we're moving. The QoS settings, it's IGMP settings, it's everything else that we normally would have to manually configure. So everything from video to audio, there's lighting presets in here, NDI presets, NDI with audio presets. There's a lot, and more coming, seems like every day or every firmware release, really. So we're going to build a Dante network. Hit next. I'm going to name it Dante, if I can type. And then I'm going to give it a VLAN ID. So VLAN ID, the name can be whatever you want to name it. It can be Alex's Happy Dante Network, whatever you want to call it. It's just an identifier for you to know what it is. The VLAN ID, however, is really important. This is the tag, the number that switches put on the packets that are traversing between switches to know which VLAN this packet belongs to. You can go from VLAN ID 1 all the way to 9,999. And it can be whatever number you want it to be. It just, you cannot have more than one, you can't duplicate them. If you use the same VLAN ID across switches, then, or across VLANs, you'll have problems. This is, when we're building our own VLANs that are contained in our AV network, the numbering scheme can be whatever you want it to be. If this is where, though, if you're trunking back to your corporate or house IT network, where you have to be on the same page with them. If your production network is VLAN ID 123 from them that they've created, you need to make sure that your production, the networked VLAN ID is VLAN ID 123. That's how you get the two to be the same, right? So we'll name this 61. Color is something just for engage. So what identifies our port colors. It has no other bearing beyond the AV UI here. Hit next. And then we're going to start assigning ports. So I need the top rack, or the bottom rack switch one. This guy. Untag all. I'm going to take it off of my trunk ports. And take it off those two. And then where else do we have Dante? We've got two Dante. Oh gosh. First time using a microphone. We've got two Dante devices on this bottom switch here as well. So I'm going to go find that. Top rack, switch 2. Put those two devices on this VLAN, or those two ports on this VLAN. Hit apply. Are you sure? Yes. And then next we need to, it's asking us, do we want to create a DHCP server? So if your DHCP servers are what hand out IP addresses to devices on the network, when you plug your laptop in to the network and get an IP address, there's a DHCP server somewhere on your network that has said, okay, Alex's laptop, you get 192.168.123, whatever. In this case, there is no DHCP server on this VLAN. It's not a VLAN we're getting from our IT department or whatever. Technically, we could run without one. It just means you manually need to go into all your devices and assign them an IP. Or we can create our own DHCP server that just lives inside our switches. So we're going to do that. The wording on this confuses me. I have to read it every time.
So the other thing that enables that VLAN routing planner is if you're doing routing between your different networks. So we talked about when does an IP packet know to go to the router. And that's where, like, say you wanted to be able to talk to devices on your kids' lighting VLAN from another VLAN in the building. If you're managing that on your side rather than the house IT department, that's kind of how you would do that. And you can set up gateways on these switches and things like that. So your managed switches have some functionality of routing in them as well. But on basic networks, that's where we're just kind of using a DHCP server, and that router IP doesn't really matter.
Product plug here, just again because it's awesome. We're not actually going through it today, but in the very top of that rack is a Pro AV router that Netgear has released that is fantastic. So if you need one of those, call Alex. Or call us. We can help you with that too. The Pro AV router, or any router in general, it's an excellent tool for if I need to connect to a house network to get internet, what have you, and if I don't have the ability to really coordinate with an IT department to properly hand a network off. Think of it just like the Wi-Fi router you might have at your house. I can plug one uplink port into a port on the wall, and it presents as one device, and then I can feed internet to all of my networks and VLANs, but only present as one device to the house network. Really powerful tool. Sometimes necessary, sometimes not. Okay, so we're building a DHCP server, right? So first thing I need to do is pick where I want my DHCP server to live, which all of these switches are capable of being DHCP servers. We only need one on any one given VLAN. Typically, we want that to be on our core switch, just because it's the one central logical point. There's no reason I can't make an edge switch be the DHCP server, but yeah, why? Same thing with IGMP Querier. Like Alex said earlier, we want the core to be the IGMP Querier. It's a little different in Netgear land, but in Cisco or some others, all of your multicast traffic has to make it to the IGMP Querier before the IGMP Querier then figures out who gets what, which means you could really quickly saturate your uplinks with multicast traffic, even if you're not actually sending this camera to that switch. So anyway, make the core switch IGMP Querier, same thing with DHCP server. I'm gonna hit apply, go to VLAN routing, and I'm gonna give this switch an address, 216.8.61.11. You'll notice I made this second octet, 61. I made that number the same number as my VLAN ID. That's just an organizational thing that we like to do a lot. It makes it really easy when I plug in and get an IP address to know what VLAN I'm on. You don't have to do that at all. You know, this could be, 161 or 123, whatever you want it to be. as long as you don't have other VLANs with the same IP range. It does need to be unique per VLAN. Obviously, that only goes so far too. You can only have 255. The highest number you can get to in an octet is 255 or 254 or whatever. But you can have VLAN IDs up to 9,999. So sometimes that logic breaks, that organizational logic breaks down. But yeah, this is defining how big I want my subnet to be. Like Alex mentioned earlier, if I put 254 in here, then I'd get 60, everything in 61 and everything in 62. 61's a valid starting address, right? That's something I have to look up.
One of the main reasons why we do DHCP servers on a lot of our production networks now that they're converged and on the same switch is it gives you a really easy way when you plug in a device to know, hey, am I on the right subnet and network? Because you know by the IP range that you're getting, oh, I'm in the Dante network, oh, I'm in the lighting network, without having to really think about it. And it's a good double check when you plug something in. What IP are you getting?
It automatically gave us our default router, which is the same as my DHCP server, which is correct. That will put this default router IP in all of the devices it hands out IPs to. And then this is where we define our DHCP range. So I want it to start at address 100 and go all the way to the end of the range at 254. This is, again, totally user definable. You could make this start at, 2 or 1 technically, if you wanted to. But if I did make this start at 2, we already may have a potential problem in that I've already got a device statically assigned to .11. There's potential for my DHCP server to hand out an address that I've manually set to something else. So a DHCP server will never hand out the same address twice until its lease expires. But there's nothing stopping you from setting a static IP address in a range and then the DHCP server assigning something else that same IP address, right? Then you have an IP conflict and, weeping and gnashing of teeth, right? Yeah, very common problem. So logically, the best way to handle that is setting my DHCP range and knowing anything under 100 right now, 1 to 99 is a static range now. I can set my computer to 192.168.61.51 and know a DHCP server is never going to hand out that address to another device. So it's important to know, even if you're getting a network from like a house IT, it's important to know what the DHCP range is so that we don't set devices to IPs in the DHCP range. Or it's really common in IT and data networks to make the entire scope DHCP because they don't deal with a lot of static devices. They may hold the first block of like 10 or 20 IPs for like their switches and hardware like that, and then make the entire rest of the scope DHCP, which is fine in a data network because people don't assign manual addresses. In production, we assign manual addresses a lot. So knowing what the DHCP range that you're working with from the house IT is really important. And then if you need to, going back to them saying, can we make DHCP over here and make this static? That's usually a really easy change for them. But just...
Yeah, I think kind of general rule of thumb, we leave on most networks half the range for DHCP and then half for static addresses. And that kind of gives you a good starting point.
And something else cool, again, going back to the subnet mask here, what we see a lot in especially church networks is if this is 254, now I have the range 61 to 62. So 192.168.61.1 to 192.168.62.254. That's my entire VLAN. It just doubled in size, right? And a lot of times in that case, we'll see a pool, a DHCP pool like this, 2 to 254. So the entire first half of the subnet is DHCP, and anything 192.168.62 dot anything is all static for us. So now we've got 1,024 addresses to work with. Half of that is static, half of that is DHCP.
Yeah. I think for this example, we'll do probably 255.255.255, and then we'll just make it 150 to .250, and that'll kind of be our start.
150, yes, sir. And apply.
Cool.
This is asking if we want to set up a DNS server. You only need DNS if you're connecting to the internet for this VLAN, in which case we are not. No, I do not want to configure.
So that kind of shows, again, it's pretty simple to set up your different VLANs. It's very visual now with the tools that we have. You don't have to dive into the command line anymore. And it's easy for you guys to take ownership over your network and not have to ask somebody else to help change ports or add a new VLAN for new devices and things like that. And again, we're not sponsored by Netgear or anything. They provide us with the switches. We just really like this product for doing AV networks. It makes things simple. So I think now that we got that done, we're going to take a quick 5-minute break. So feel free to grab some coffee, and then we're going to dive into some different media protocols after that. Cool.
Good.
Guys, we are going to move pretty quick, so don't go too far. Everybody, as well, if you didn't get a gift bag over the table over there, feel free to grab one before you guys leave. Thanks again.
All right, so we're going to start back up just because we're moving quick. Now we get to talk about some of the fun stuff. So what does that look like in your networks? So we built our Dante network. We're going to kind of look at just a quick thing of naming devices in Dante controller. Actually, let's bounce that quick.
Switch me off.
So one thing that you might notice after you create a VLAN is that devices might not get an IP address right away. So usually when you create a new VLAN without unplugging and patching back in the device, kind of what we did, that's where you have to kind of bounce power to devices, which we'll do in Netgear Engage here in a second.
Okay.
Cool. We're good to go.
So my computer's now got a DHCP address from the range that we set a minute ago, .61. And we can see, oh, yeah, I know, go away. We can see devices have started to populate already. During that break, we rebooted all of these Dante devices so that they'd all get fresh IP addresses. So real quick, we're going to do a quick walkthrough of Dante controller, some do's and don'ts with it. First thing to note with Dante is just the first thing to do when you set up a Dante device is name it. Name it, name it, name it. Name the device, name the channel. Dante does its routes by device and channel name, not by IP address, not by MAC address, even though those are the tools it uses to make it work in the background. So I've just opened up this device. You know, if this is stage laptop input, you know, name it something logical. Name it by room name, device name, or room name, what it does, or
Yeah, this just helps you as you grow your network. It's really easy to throw stuff in, start routing things, but again, your routes are going to break if you rename a device after you've made those routes, because Dante does its audio routing based on the device name and the channel name. So like an example here, I think, did we just rename a device? You'll see a little yellow check mark saying, hey, as soon as you reboot your devices, it's going to break the audio route.
Yep.
Because you renamed it. So, which is also cool because you can take one device with the same name, unplug it, plug in another device with that name, and then everything will pop back up.
Yeah, exactly. If this USB device died, I could disconnect it, plug in a new one, name it the same thing, and all my routes would reestablish. Just to illustrate that real fast, we can see this device, Clark KG AVIO USB. Channel left, we have routed to a mystery device named Atrium Monitors. You can see in this pop-up what it's actually doing. It's routing channel left at Clark KG AVIO USB to channel 1 Atrium Monitors, right? That is the actual route, the device name. So if I go in here to this device, change its name to USB 2, we're going to watch this route die, if you will. There it goes. The TX channel name is changed, and the subscription, these pop-ups don't last nearly long enough, may not be reestablished. It can't find that device and channel name on my Dante network anymore. Physically, the hardware's still here, but it can't find it. So if I go, and vice versa, if I go back and rename it to the correct name, it already did it. That route reestablishes. So name your devices first. If you do all of your routing and then decide to name your devices, you get to do all of your routing again. Just get a lot of good practice at it.
So one thing we talked about before, again, was that unicast versus multicast traffic. And that's going to apply, again, with Dante, with NDI, with any sort of network media protocol. Kind of knowing these terms is going to help you. And one area with Dante is that they show basically each device can only handle so many flows out. So on a small device, that's where like an AVIO can only do 2 or 3 flows. So I don't know if you want to show
Yep.
on an AVIO kind of our maximum flows for unicast.
So again, this device is this AVIO USB interface, right? If I open the device and go view flow information, you can see I'm currently sending 1 unicast flow, which is, can't see these side by side. View, not what I wanted. There we go. Which is this 1 stream from the AVIO USB to the Atrium Monitor's AVIO. Doing 1 unicast stream, no multicast, a total of 1 of 2. That means this device is capable of sending 2 flows. A Dante flow can contain up to 4 channels. So if I send the second channel, wait for it to establish, view flow information, nothing changed here. I'm sending 2 channels, but from the same 2 devices, from the same device to the same destination, I mean. So it's still 1 flow. If I send this to a second device, we're now using 2 of 2 flows.
So kind of what we're going to do is to offload that. What we talked about before with the switch basically managing that is now we can create a multicast flow, which is only going to be a single stream from our device. So we're not going to use up our limited amount of flows. So if you want a demo on there, kind of the multicast flow, what happens when you create that?
Yep, so if I were to try and make a third, send this to a third destination, I'm going to get a problem. It says no more flows. I'm out of available flows. So I go back into the transmitter, use this little button up here that says create multicast flow, pick the channels that I want to add to that flow. If this was like a stage rack or something that had 48 inputs, you'd see all 48 here. You can only add up to 4 channels per flow. Then you have to create multiple flows. But as soon as I hit create, we should see this problem resolve itself. And there it goes already. And now, if I go to view flow information, sending 0 unicast flows, 1 multicast flow, and now I'm only using 1 of 2 total flows. So now, instead of this device trying to send out 3 audio streams, it's sending out 1, and the switch, our network switches, are duplicating that traffic and sending it to all the destinations that are requesting it. And honestly, it could pretty much go unlimited at this point. I can send it to as many destinations as I can connect to my switches.
Yes, and the reason why that's not enabled by default is because of IGMP snooping that we talked about, in that because we're not doing multicast flows by default, it's going to work on a basic non-configured network. Whereas if you start doing a lot of multicast flows, you need to make sure that you have IGMP snooping enabled on that. The next thing we're going to look at is clocking. Yes.
Just so that on your, like, when you're showing then, like, your switch or your network, your switch, so now that bandwidth, upload, download, or whatever it was, is that going to be showing on all of those?
No, because we're using IGMP, and IGMP is the tool.
Yes.
We'll send that audio traffic only to what wants it. Yep.
Yeah.
Yep.
Cool. So
If you don't have IGMP enabled, then yes, all of your ports are getting all of that traffic. And that's where you get into problems of saturating your ports.
Cool. So next thing we're going to look at clocking. So you guys remember word clock, you remember video gen lock, things like that. That's where that's been replaced by the network version, which is PTP. So with PTP, it's a similar clocking structure to what we were doing before. So we have a leader clock and we have followers on the network. Again, we need 1 device to be that leader clock. And that's usually, we pick a device that's not getting turned off and on a lot, and something that has a stable chipset. So there's 2 different versions of PTP. There's PTP v1, which is what Audinate initially used, and then there's PTP-v2, which is what we use now for broadcast video with SMPTE 2110, and some other manufacturers use that as well for things that require precision timing. Add some different profiles and some additional features that make it work for those things. So with PTP, what happens when you basically start plugging in devices on your network, it's kind of like this floating table of metronomes where all the devices come online and they all have different clocks. Each device has an individual clock that isn't synchronized to anything. But eventually there's this thing called the best master clock algorithm, where it's determined by, does the clock have a different priority value that makes it basically higher up in the chain to get elected? Does it have GPS sync? Different things like that that allow all the devices between each other to elect a leader clock if you don't have a preferred leader set, which is again using that priority is part of that process. So then eventually, after all those packets have kind of gone on the network and the leader clock is identified by all the devices, that's where all your devices then start to be in sync, because all the internal clocks of each device, just like all the different metronomes on this table, are synchronized to one device on the network. And this is down to a nanosecond, less than a nanosecond of accuracy, so it's good for whatever clock sample rate you want, can be derived off that, video reference, anything of that nature. We'll move on from there. Again, this is kind of an example of some of those synchronization messages that initially happen and are also happening periodically on the network from each device. One thing that's kind of happened now is that our switches are playing an active role in clocking on larger networks. This is more for devices that require PTP-v2. But our switch can actually intercept those PTP packets and add a correction time, which we'll look at in a second, that helps correct for the latency that it takes to move through the switch. Just like with kind of broadcast traffic that we talked about, it can be a lot of clocking messages when you start to build up a network. And now you have the ability for the switch to take some of that workload, where the switch itself is synchronizing to your PTP leader clock, and then the devices connected to your switch are then synchronizing to the switch, and they view the switch as the master, and then the switch itself is synchronized to whatever master clock that you have. Still kind of rare, but
I was just going to say that transparent clocking is something else where designing a network properly, we got to start from the right place. A lot of switch manufacturers don't do PTP transparent clocking.
yeah. So we're going to look at kind of our network with an app that I like to use called PTP TrackHound. And this is a great way to see PTP on your network when you have a mixed environment with Dante devices as well as other devices. So on our, let me start live capture. So we see our network kind of building right here, our devices popping onto our PTP-v1 clock. So this is our clock domain here, and then we have a device acting as a boundary clock, this Dante device, to provide PTP clock to this Crestron unit, which is doing AES67, and that's PTP only. So what that looks like in Dante controller is going to be, we'll see we have our leader clock up here, and then this is our device that's acting as a boundary clock. You can also have a device act as both your PTP-v1 and v2 master, but that's kind of boundary clocking and what that looks like on the network. And then we can also see, which is kind of cool, on our packet capture, we can see on a PTP-v2 message.
You need to switch here.
Yeah. Our inconveniently placed video switcher. We can see, oh, I don't think we turned on transparent clock, but there is a correction value here in that PTP field that you would see if transparent clocking is turned on. You can see that nanosecond correction time is added to your packets. So with PTP, again, the main thing is look at your clocking hierarchy, elect something that's on most of the time. A perfect example of this is a lot of people like to use their front of house console as their PTP leader clock. In a fixed situation, like in a church, that's where you're turning off and on that console all the time. So you may not want that as your PTP clock master because you have a QSys core sending audio to your lobby. Every time that switch boots back up, or the front of house console boots back up, everything on the network is going to try and sync back to that console because you've elected it as your leader. And audio is going to drop if the difference is too big between what the current clock was and what the internal clock is of your console. So that's where it's a little bit different than the touring side in that you might not want to have your front of house console as your leader clock because you have other devices that are on all the time passing audio that require PTP. So having that jump back and forth may not be a good thing. Cool. All right. So we're going to touch briefly. NDI is another streaming protocol. We're using that on the Kero switcher right now. I don't know if you want to bring that up, Bob. So you can see we have some NDI streams coming from cameras, ProPresenter for key and fill, things like that. That's where NDI is kind of a really effective and easy way, just like Dante, to send video over your network for smaller setups. Latency is going to be something to keep in mind because it's not locked to something like PTP. But it is a great utility way to send video or do a small setup. For this, that's where, again, those same concepts apply to whatever streaming protocol we're talking about. Unicast, multicast, things like that. There's so many different ones now that we decided to kind of pare down what we talk about.
Yeah.
Dante is kind of a great example. But if you guys have questions about specific protocols, feel free to ask us afterwards. On the broadcast video side of things, that's where 2110 has become common. So for me on the live side of things, doing shows, that's where on large scale systems, we have 2110 trucks that pull up, and they're interoperable. I can grab a fiber cable, connect the A and B units, share resources, pass things between them, all over an IP-based connection, which is amazing. And Blackmagic came out with a bunch of 2110 devices this year at NAB. So we might see kind of 2110 start to move into kind of the church market as well as devices become cheaper and the tools for them become easier to use. It's a little bit more complex than something like NDI because you do have to deal with PTP, which is what we talked about. And there's a few more kind of layers of management and control that you have to think of with that. But 2110 helps define the standards for all the things you need in broadcast, like tally, closed captioning, device discovery and registration, compressed and uncompressed video, and it's also low latency and locked to PTP. So that is something to kind of keep in mind down the road as we kind of look towards building networks that are compatible with that in the future as it becomes readily available. The last tool that I wanted to show is just a really simple tool, and it's network scanning. So there's a tool that I like to use called iNet Network Scanner. And what it's doing is it's sending kind of basically a ping request like what we looked at before. And this uses a lot of the things that we talked about. So the MAC address of the device is how we're identifying the manufacturer. And then it's scanning our subnet range as well. And then I can see what services each device has. So I can go to the web page of the device directly from this if I want to, which I think that's an old scan.
We didn't set up a IP for that switch on this VLAN yet.
So it's another tool to help you troubleshoot and have visibility into your network of what's connected when you plug in. Cool. So I think that is it. We want to leave a little bit of time for questions for you guys. Thanks for sitting through that. I know it's a lot of kind of the IT-centric knowledge, but I hope that gives you guys a better base to talk about IP principles and kind of an insight to the different terms that our different AV devices use. Anybody have questions?
Yeah, back.
More and more stuff is moving to using IP6. What are we doing with IP6 in the AVL world?
In the AVL world, we've seen devices support IPv6, but for the most part, it's still using IPv4 for logical addressing. Even in large-scale broadcast networks, that's where, for the most part, it's still all IPv4. And I don't really see that going away because there's not a need for a large range of addresses in some of the feature set that IPv6 offers. So for the most part, I kind of see us living in that IPv4 world.
Yeah, the reason 6 exists is because we've run out of addresses of v4 on the greater internet, right? Our corporate networks are not, there's not enough devices on them to run out of v4 addresses, so. A lot of stuff supports it. A lot of our AV stuff supports it. We just, I don't like typing all those numbers in, to be to be honest.
Yeah, yep. And it takes a little bit more knowledge of setting up IPv6 just
true.
because that's not an easy one-button thing on a lot of devices. So, cool.
Yeah. Yeah.
Can I get a Netgear core switch and use those existing Cisco switches as leafs and take advantage of the Netgear Engage configuration, or do I need Netgear on the core and the leaf?
Sort of.
Yes and no.
There are a bunch of things are universal between manufacturers. One of the things that's not necessarily universal is IGMP. So sometimes different switch manufacturers don't play well together with IGMP. So it's something that you could do that as long as IGMP is not enabled, and then see if you enable it and it does work. That'd be the only thing I'd be wary of. But you won't actually see all of your Cisco switches show up and engage at all.
Talk to Alex, he says.
Yeah.
Alex is back in the back. So Alex is the guy, for y'all's reference, Alex is the guy that we call when we get stuck. He's one of Netgear's Pro AV design engineers, helps build the platform. So yeah, any questions you have, please, even afterwards, let us know. Also, Alex is a great resource. So yeah.
Yeah, what would be like a best practice if you had a device that needed like a converged space between two VLANs? Like, for example, like we use Resolume that brings in like NDI and like DMX data from our lighting network.
Yeah.
Like, QSys that would use like the visionary solutions control.
Yeah, so the question is, what's the best practice if I have one device that needs to talk to multiple VLANs or get data from multiple VLANs? And that's where either routing between those VLANs is something we would set up so that we can, that one device can see and talk to things on multiple devices. Some data will not traverse a VLAN, like Dante. You cannot route from one VLAN to another VLAN without Dante Domain Manager and a bunch of other stuff. But in which case, maybe you want to add multiple network cards to that Resolume computer. That, by default, that's what I would tell you to do, especially with Resolume, that specific example. Put a network adapter for lighting to get to your lighting control, put a network adapter for audio to get audio in and out, network adapter for NDI, and make those all come on different physical ports on the computer.
Yeah. The problem is with earlier versions of NDI, you couldn't choose which NIC you were using for the NDI stream, and that's kind of where we ran into issues, but just something to be aware of.
Yeah.
All right, one
Back
from
in
the
the
back.
Yeah, can you talk a little bit about what PTP time residency stamping is, and if that's something you've had to deal with? I know we've had it turned off on our network, and that's been the most stable, but I'm just wondering what the purpose of it is.
So with PTP, PTP v1 really doesn't interact with your switch with PTP transparent mode, or there's a few different terms. There's the residency stamping of how long it takes to go through the switch. With PTP v2, that's where then some switches play well having PTP v1 and PTP v2 with transparent mode engaged, some don't. What type of switches do you guys have right now?
Netgear.
Yeah, Netgear, it's fine to turn on the E2E transparent mode. So it's not really going to help you a ton on the Dante side, but if you have other stuff like Rito Bolero or ClearCom or things like that, that's where that can add some stability with that.
Anybody else? Yeah.
Yeah.
Run, Jeffrey.
I guess kind of a follow-up. So, Cisco has a proven track record. So with Netgear, what is your take on Netgear's track record with these type of AV switches? I mean, it's a fairly large investment to switch over. It's a great product, but what do you track record, I guess, is the question.
So yeah, so Cisco, for your reference, before we started doing a lot of Netgear, Cisco SG was what we would deploy most of the time. It's still a fantastic piece of hardware. As far as Netgear versus Cisco track record, if you will, what I would say is yes, Netgear may not be in the AV space for as long as Cisco has existed in the corporate space, but I'll tell you this, when we have problems, even with Netgear hardware, we can pick up the phone and call somebody and say, I'm doing this with Dante and PTP, and immediately get to somebody that knows what Dante and PTP are. With Cisco Extreme, name your manufacturer, the AV market is such a niche market for them that finding an engineer that even is familiar with exactly what we're trying to do may take a while, right? If you think about the AV market for Cisco, it's a drop in the bucket compared to their corporate, network market. That's what they're focused on, which is great, and they make great hardware for that. Netgear has developed a market that is specific and here to support the Pro AV team. I don't know if I could speak for Alex, but Alex, I think you only do AV related stuff, right? Yeah. So they have an entire team specific to our industry for that kind of support. So
Yeah. But again, Cisco works. It just takes a little more
does.
knowledge to configure and make it work well.
It all goes back to the system design and just not assuming that any one network switch is just going to work because it's a network switch. They all do different things differently, and making sure we're using the right tools for the right job. And you don't have to switch your entire church network over to Netgear. Keep all the corporate stuff on all your Cisco stuff. If that's working, or Ubiquiti or Meraki, whatever, if that's working, do that. The AV stuff, if you're having problems, like let's talk about designing an AV-specific network with AV-specific network hardware.
Cool. Yeah, I think we'll take one more question, and then we'll be around for all of FILO, so feel free to come up and ask specific questions if you guys have them. But yeah, anybody else have one more question to close us out?
Yeah, in the back.
Early in the talk, you guys were talking physical infrastructure and cables and testing cables.
Yeah.
Maybe I missed it, but if we're looking at SDI infrastructure, are there any good, inexpensive tools for testing installed SDI, coax? What are we doing with those to figure out where we're failing in SDI world?
Okay. In the SDI world,
Talk to Bob Baker.
There's a guy back
Bob
there
Baker
named Bob
back there
Baker,
running the
and he can
switcher.
give you a brain dump on everything. Those tools are generally a little more expensive still to do actual physical analysis of SDI, but Bob would love to talk to you about that.
We have a joke. He has a $20,000 rasterizer that he carries around with him.
Yep. Very proud.
He will let you know.
Yep. Cool. Well, thanks again, guys, for coming. I appreciate you guys coming out, taking the time to learn. Yeah, let us know if you have anything.